Perfect. Now I turn this off. Okay, so we're finally ready to get started. So we have Louis Topley from Bath speaking about equivariant symplectic resolutions, right?
Equivariant deformation.
Deformation theory,
The
right?
nilpotent Slodowy varieties.
Equivariant deformation theory and nilpotent Slodowy theory. Thank you.
So, I would.
Equivariant deformation theory, yes, for nilpotent Slodowy theories.
Have the other, So, thank you very much for the invitation to come and talk about my work. And hello to everyone at home. So I didn't know beforehand that I should tailor it all towards quivers, so I'm afraid I haven't, but I can try and mention some relationships that I'm aware of in order to kind of make the
Well,
the
people
subject matter.
are definitely interested in nilpotent, for nilpotent orbit closures that
Yeah,
you
sure.
manage.
So oh yeah, thank you. So the connections to symplectic duality, which I'll mention at the end, they involve nilpotent orbits and their couples and their affinizations.
See, these people here, some of them that know about ways of realizing many of these nilpotent orbit closures via quivers.
Right, yeah, I saw your talk in the RepNet seminar during the lockdown, so I was sort of aware of your zeal in this work, yeah, but yeah, there's quite a lot I'd like to ask you about that actually. We can save that for after that. So the overview of the talk is that we have the functors of Poisson deformations. So this is a very classical construction, and in the context of conic symplectic singularities, it's a very powerful tool that was used by Namikawa to show that there is sort of, if you want to understand all the Poisson deformations of a conic symplectic singularity, then there is some sort of universal gadgets which, from which every other Poisson deformation can be obtained by base change. I'm going to state this very carefully with definitions. But the other part of this is quantization. So this is something which is not, I don't think it's appeared in the literature before, but it turns out that there is actually a functor of quantizations of Poisson deformations. And there is, a very important result of Losev, which says that this universal Poisson deformation of Namikawa can actually be quantized. And as well as, describing how to construct this quantization, he showed that it had a very special universal property. And so in my sort of trying to understand his work, we rewrote his theorem in a more kind of extensive language, and we introduced the functor of quantizations and showed that he was really giving an initial element for a functor which he hadn't explicitly written down. So I think this is an interesting point of view to take. I'll say who my co-authors are in a moment. So dressing everything up in a categorical language is maybe a sort of questionable activity if you don't see some kind of some immediate use for it. And we did find a use straight away. So by expressing things in this, functorial language, it became very clear how to describe what happens in terms of equivariant deformations. So there were some hints of why this was a good thing to do in the work of Slodowy. That was our main motivation for introducing this formalism, but it also becomes interesting in the setting of nilpotent Slodowy varieties. So in the third section, I'll talk about Slodowy slices and finite W algebras.
So it's the idea that, given any singularity and some automorphism, then instead of considering the universal deformation, you consider the universal equivariant deformation, and that you have different appearances of the same singularity where the natural family is given by this latter thing.
Exactly, yeah. So our kind of way of making this equivariant stuff kind of natural and interesting was the question. So these Slodowy slices and finite W algebras, they give you deformations and quantizations of a certain natural object, this nilpotent Slodowy variety. And the question is, when is this the universal equivariant deformation? So you're given one by some kind of magical construction, but does it satisfy the universal property? And the answer is almost always yes. And we found that in the cases where the answer is no, it's sort of corrected by looking at things in the equivariant setting, which is, I think it sort of hints to something deeper, but I mean, this is just the beginning, I guess, of understanding the full picture. So my co-authors are Filippo Ambrosio.
Is there a relationship between this and looking at deformations of the quotient by the group of automorphisms? Because there are situations also where, you take a singularity which doesn't admit, say, a smoothing or a deformation, but its quotient by a finite group does.
Right.
Is there any relationship to that?
Well, I expect there should be, but I don't have anything concrete in that direction. Let me think for a moment. So,
You have some examples with symplectic and
Right, exactly.
okay, right. I don't know. I've studied. Some of my work has been about looking at the fixed points of certain conic symplectic singularities under finite groups of automorphisms, and I know quite a lot about the connections there. Although again, I don't have any general results. But I can sort of equate the fixed points with Poisson structure using what I call direct reduction. And I'm interested to know whether this sort of fits into some sort of categorical framework. The last person is Francesco Esposito. I think there should be some connection with this quotient. And there's some indication of that in the very last part where I talk about the sort of symplectic jewel of our main theorem. So we're going to take a finitely generated complex Poisson algebra. In fact, all the algebras are going to be finitely generated over complex numbers, and this is going to be graded in degree minus d. So that just means that if you consider the Poisson bracket here, and you take the I graded piece, the j graded piece, then this goes to the I bracket j minus d graded piece. So this is okay, so the grading is also connected. This means that and non-negative. So this means that A is the direct sum of its non-positive, so non-negative class, and so that the zero graded part is so these are just some properties that conic symplectic singularities, or rather their coordinate rings, have, and the formulation of this deformation functor and quantizations they probably set up in this generality, but they only have interesting properties.
you allow for any t.
Yeah, any positive.
The case we know the most is -2, so d is equal to 2.
Yeah.
But you say you could just do rescaling.
Well, I guess this grading implicitly I'm assuming that it's a Z grading, and it's not always possible to scale to -2 and keep within the integers. But if you're happy with rational gradings, then you can always assume D is -2. But I think that Namakawa showed that if you look at the class of all conic symplectic singularities with a fixed D and of a fixed dimension, then there are a finite number of them up to isomorphisms. So somehow, sort of not rescaling with these, it retains a bit more information.
Let's see. You know what the algebra will give you equals 1.
Somehow, yeah, different needs are possible.
Yeah, different
Yeah.
needs are of course possible, yeah.
Although Namakawa says that the correct D for the Lie algebra is actually -2. And the reason is that
Two,
sorry, it's 2, yeah, D equals 2. The observation, I suppose, goes back to Konstantin and Brzezinski, is that if you take an orbit closure and then you take its normalization, then well, of course, the orbit closure will always have things in, you know, you can take the bracket in degree -1, but if you want the orbit closure, this is the slightly larger algebra, and you might get things coming in degree
normalization.
up. Yeah, you take the normalization.
Normalization will be large, so if you start with things in degree 2, when you normalize, you can get things in degree 1. While if
Exactly,
you start
yeah,
at degree 1, you get things in degree 1.5.
exactly, yeah. So if you want to stay with it, if you want your, you know, your gradings to correspond to C-star actions in a sort of honest way, then perhaps 2 is the better number, for, even for the sort of people who use it.
I think there's another reason, but anyway, yeah, there's some multiple reasons why they say you should think about it as in degree 2. And I guess this is what you get from the Fulham point of view as well.
Yeah.
Okay.
So we pass with, we call it passing,
Yeah.
and that's the maximum.
So, let me introduce a bit of notation. So this is going to be roughly all the adjectives that I just put there. So it's the category of non-negatively graded, connected. So this is roughly connected. Actually, this is not Poisson. This is just commutative algebras. So these are going to be the basis for deformations. And I don't think, I suppose I need also so this is the category which will form the basis. And let me just say what a Poisson deformation actually is. So we've got chosen our Poisson algebra or equivalent to some Poisson variety. A graded Poisson deformation. Color A is so it should be over a base over a fixed P. This is the following data, so just sum A iota, and here A is a flat graded Poisson B algebra. And it should have the property that iota is a choice of isomorphism from central fiber to A. So again, I'm making up more notation as I go along this. So B, because it's a connected, non-negatively graded algebra, there is a unique graded maximal ideal. And this is the, so this complex numbers is the sort of one-dimensional representation given by this unique graded maximal ideal. So we can tensor over this base with this one-dimensional, and the idea is this should be isomorphic, and we fix an isomorphism. So geometrically, you can think of this as a family of algebras over spec of P. I suppose I should mention that when I say it's a graded Poisson P algebra, I'm assuming that so P is going to the center of this Poisson algebra. This means that spectralizing a maximal ideals of B will give you another Poisson algebra. So this should be an isomorphism of graded Poisson algebras. And you know, if I was to take any other maximal ideal of B, then I could specialize there, taking the sort of geometric fiber at that point. And this is just some other Poisson algebra. It's another Poisson variety which lives in a family. This grading is equivalent to a C-star action, which is contracting everything down to the points corresponding to this copy of C. Okay, so the first example I ever learned about is the case of a semi-simple Lie algebra. And it's nilpotent cone. So how do we deform nilpotent cone? We can take B to be the G-invariant functions on G star. We take A to be just the functions on G star, that this is the Poisson algebra. So it was observed that G star is a Poisson manifold even by Sophus Leave. All Poisson algebras were introduced. And the deformation that's going on here is if we take the so there's a theorem of Poisson. It's not very hard to sort of see in special cases that if you take in G star, this is the image in so this is contained inside G star. It's just the image of the nilpotent component. And this is under an identification made by the Gilling isomorphism. So we have a non-degenerate form. And this is the algebra allows us to identify G and G star as G modules. So we've got this set here, and Cotton showed that if you take this large Poisson algebra and you specialize over the maximal graded ideal of the invariant functions, then this is isomorphic to the coordinate ring on the null cone. So what's happening is this is the conic symplectic singularity, or this is the nice graded Poisson algebra A. This is some large Poisson algebra curly A, and then we're deforming it over this thing, which turns out to be the Poisson center. So you can easily see that there's an isomorphism like this in the case of GLN, because these invariant functions are just the coefficients of the characteristic polynomial. So nilpotent matrices are defined precisely by the vanishing of those coefficients.
Why are you calling this deformation?
So this is a deformation because A is assumed to be a flat B algebra, and so the sort of geometric picture would be that we have so spec A, there's a flat morphism down to spec B, and the central fiber, I guess I should say, central fiber charge is denoted by 0, and then above this you have spec A, so this is our Poisson variety that we're trying to deform. This includes in here. So the fibers of this morphism deform the central fiber, which is the guy that we started with.
Right, so I guess in general, if you just have a morphism, you can think of it as flat morphism, and you can think about it as a flat deformation of, say, a particular fiber to other fibers. That's what it means.
Yeah, you should. So the original definition of flat in the sort of homological sense is a bit of a it's a bit deceptive. You know, it's really the point is that the fibers of this map, if you're if the base is going Macaulay and you're working over the complex numbers, and then the fibers they have the constant dimension if and only of the morphism. So it's really just asking for the fibers to be have constant dimension.
Yeah, but you have this homological property of flatness, which is nice. So. And somehow locally, you're going to get the same vector space. Yeah, I guess it's sort of the general philosophy of algebraic geometry. I mean, when they talk about families of something or deformations of something, it's just a morphism. Of the total space mapping to the base.
So if you take J, using G as SO2, can you show how you get from the left-hand side to the right?
You mean up here?
No,
Sorry. Down here,
Yes.
right? Yeah. So let me think. There's only one invariant function here, and that's the determinant. Yeah, because the trace is already vanishing. So if we ask for the determinant to vanish as well, that's what we're doing by taking the tensor product. It's just specializing at the vanishing modus of the determinant. Then this means that we're looking for elements of SL2 where all the coefficients of the characteristic polynomial vanish. And that's the same as asking for nilpotent matrices. Yeah, and in fact, I suppose the part of this that's slightly less clear is that these are precisely the defining equations of the nilpotent code. It's possible that you could have a non-reduced kind of specialization, but this is a reduced, this is a nice model. And then there's another bit of sort of general algebraic geometry, mumbo jumbo, is that deformations are captured through a functor. So we consider the functor which takes graded algebras with all of these properties, and it sends them to isoclasses of Poisson deformations over B. So that's, I guess it's quite hard to think about all of these things at once, but you don't really have to. I suppose just accept that this is well defined. In order to make it clear that this really is a functor, I should say what we do to morphisms. So if I take any isomorphism class of these Poisson deformations over a given base, and I have a map to another base, then I can just tensor through this map. And this is just called base change. So we're just now looking at a new deformation. Again, we don't know what it is, but it has the right properties. So fine, we have a functor. The reason this is a powerful tool is that I'll prove the following theorem, I think in around 2010, 2011. So if A is the coordinate ring of a conic symplectic singularity, should I say more about what that is, or has everyone seen this in the seminar series? Yeah. That's really the first step. Okay, and the amazing thing is that PDA is representable. I'm going to unpack that in a second. It's representable over some algebra, some special algebra BU, and well, actually, Namakawa showed that BU is the coordinate ring on a certain affine space, and that affine space is the invariance in some cohomology. This is the second cohomology of the regular locus of a two-factorial terminalization. I don't need any of these definitions, but I thought it was worth writing them down. And of course, I should take the file group invariant. There's something called the Namakawa file. So there's some really technical ingredients involved in this proof. And let's just accept the statement as it is. He actually proved that the functor of so there's a sort of formal Poisson deformation functor which goes from graded Artinian algebras to Poisson deformations, and he first of all showed that this is pro-representable, and then in the case of the contracted Caesar action, you can obtain the representability of this functor here. So these, rather than the deformations he was originally considering were infinitesimal deformations, but by showing that this is sort of unobstructed and pro-representable, he was able to get these global deformations. But what does it mean to have an initial element? So it means, well, I mean, quite literally, it means that Om in the category of graded algebras from the new blank is isomorphic to the Poisson deformation. Okay.
Well, is it easy to compute this, please?
No, I think every single example requires a lot of knowledge of the geometry. I mean, especially this two-factorial terminalization, they're hard to understand, in my opinion. The dynamical well group is very hard to compute. You have to know that all of the codimension two symplectic leaves inside.
The singularity.
I think inside the singularity, yeah.
You need to know a little bit more than that, but if you know what the slices, the equivalent to two symplectic leaves are, you know what the product of values is up to this folding of the factors.
Okay. So, can you explain this?
Well, it's quite simple, like you look at all of the codimension 2 strata, so all the connected symplectic leaves of codimension 2, and for each of them you have a slice, which is a Duval singularity gets dimension 2, the slice of the leaf. And this has to be of type A, D, E, because those are all of the ones you have. But so that means you could have a product for each of the corresponding group, let's say AN singularity with the AN value, you could take a product for each codimension 2 leaf of those groups. But sometimes this is not what you get. Sometimes the type A folds to a type B group, or the type D folds to a type D group, or the type E folds to a type F or G group.
Okay.
So you have to check the monodromy. It's the monodromy that you go around this codimension 2 leaf of this, say this resolution, the cohomology of the resolution that tells you whether you're folding. Because it's a cohomology of this resolution of the Duval singularity, which is the reflection representation of this group. And if you go around, you could have monodromy, which corresponds to folding the thing can diagonal.
I see. So this would be a physically interesting.
Yeah, so this is what you get. So we've talked about a little bit about this about the group, and we can talk about that more. But I guess this is not.
Yeah, I mean, I would love to know more about it. I think people in the room know far more than me. I know what it is in the examples I've worked with, and I don't know anything more than that. But so the representability, just nothing quite simply with these functors are isomorphic, but this functor is really, really nice. So the point is that if you have, if you've got any automorphism, so
Sorry, let me just say one more thing. So as a result of this, if you're already have no codimension 2 singularities, then you're just taking, there's no W, so it's just taking the cohomology. So what this is saying is, I was saying to Amitai before the talk, is that you have a Galois covering of the base of the universal deformation of the Q factorial terminalization and the universal deformation of the original thing. The covering is the Galois group is W. This is why it's sometimes called symplectic Galois group. That's what Martin called it. Right.
So yeah, the great thing about this functor on the left here is that if you have any automorphism of the base here, then every morphism say PU to C is obtained by composition. So, because we can always get any given morphism by composing with this thing up here, it means that whatever Poisson deformation is associated to that, every other Poisson deformation is obtained by base change from this one. So there exists some AU, AOCU, such that graded Poisson deformation this is a really remarkable.
Are you requiring the existence of one automorphism?
So if you take any automorphism, I mean, so you could take the identity here and then no, what do I want to say? So I think that the universal deformations, they are conjugated simply transitively by this automorphism group. So you can choose one of them, but you can choose another. They're all related by precisely the automorphism that you choose. But they're all related to the identity back to another.
So you can always choose identity.
Yeah, the identity would be a perfectly good choice. I said it in slightly greater generality because then it's slightly clearer when I say something later about the quantizations. But you might as well choose identity, and that is the convention when people talk about initial elements of functors. They usually say this is got a given one. So back to the example. So it turns out that CG star with the iota that I gave you a moment ago, this is the universal Poisson deformation. I was going to draw a picture of them. You've probably seen it on those things before. So for the case of SL2, you can just, I mean, you have that. Okay, I'll put it up. You know, the invariants are just a small bit to CH star. W. So this is just what we bring on the outline line in the case of SL2. And the picture that we have is that at the central fiber, the nilpotent component is actually just the classic component, is if you take sort of intersection with the real part. And away from the central fiber, these fibers always look the same. They're smooth varieties. So now I can talk about quantizations. So we're going to keep A as above, and now we're going to introduce another category of algebras. So this is what I call the strictly filtered algebras, and this is some adjectives. So actually, there's an easy way of saying it, which is the essential image of the functor that goes from graded algebras to filtered algebras. So what does this do? If you take some graded algebra B, which is the sum of these non-negative parts, then you can output an algebra which is filtered, and the filtered piece is just the sum of the first I filtered pieces. So not all filtered algebras have this property. They're a special class, but they are the correct thing to consider if you want to look at the base of the quantization of the Poisson deformation. So morally, this just means that we're interested in algebras which have a filtration which is non-negative and has the zero part is just the complex numbers. It's finitely generated, but it also has this property here as abstract algebras. So to give you an example, but a bit similar to the running example, if we take B to be the center of the enveloping algebra of this complex semi-simple algebra, then we learn by the theorem of Paris-Chandler that this is isomorphic to some dot invariants. But again, it's just a polynomial algebra. So polynomial algebra will ranking variables, and the filter degrees line up with the graded degrees in this invariant ring here. And so when you take the associated graded algebra of this with respect to its filtration, you get the same algebra back. So this is an example of a strictly filtered algebra. So a quantization of Poisson deformations. So I'll suppress this when I say it later. So quantization of a Poisson deformation over B. No, so it's of A over B. So A again is just some graded algebra of negative degree. B is now strictly filtered. So given by two pieces of data, so we have A iota and K should be a flat filtered B algebra. So again, assume that the structure map that goes from B to curly A maps to the center of this algebra, and it should be almost commutative. In degree minus D. So almost commutative, this means that if you consider commutators, then this takes things in filter degree I of A, in filter degree J of A to things in filter degree I plus J minus D. And the point is that when you have an almost commutative algebra which has this property, then you can equip it with a Poisson. You can equip a graded algebra with a Poisson structure. This is just by remembering the sort of the top degree piece of every commutator. That gives you a well-defined Poisson bracket in degree minus D. And we should have that A iota is a Poisson deformation over B.
So can you say again what's almost commutative?
So this means that when you take the bracket, the commutator between two elements in filter degree I and J, then so in principle, because you're taking product in degree I and J, product the opposite way of degree I and J, this definitely has to be in degree I plus J, but we're insisting that the degree actually drops down. So just like in the enveloping algebra, it drops down by 1 or 2. We say that it should drop down by D. If it happens to drop down by D and you go to almost commutative a degree D minus 1, then the Poisson algebra that comes out will be trivial. But if you have any non-commutative algebra, there is always a maximal choice of D, and for this, the brackets will be non-trivial. Then we can introduce the functor of quantizations. Okay. This is introduced. It's CT. So it's about strictly filtered algebras to sets, and it does the same thing as the functor of Poisson deformation. So it takes B to the iso classes quantizations of Poisson deformations over B. And then the theorem, which sort of got me interest started in this whole field of conic symplectic singularities, was the theorem of Losif, which we mentioned before, and which we sort of spent quite a long time understanding and adding more detail to. So this is the form that we write down in CET. So if you have a conic symplectic singularity, so I didn't actually say there are two papers that I'm surveying here. The first of them is ACET. This has just been published in the Journal of Non-Commutative Geometry, and then the second one is a paper with Ambrosio. So it'll be called AT, and that's just come out recently on the archive.
ACT stands for what?
So that's, sorry, Ambrosio, Carnevale, Esposito, Topley. I meant to say at the beginning that there are two references and they'll be denoted like this.
Oh, I see.
So this is the first of our papers that I'm talking about. So if you take the coordinate ring of this conic symplectic singularity, then Leibniz's theorem essentially says that QA is represented, or is representable, and it's represented over the same base. BU. So BU, of course, was a graded algebra, but I explained that there's a natural way of graded algebras, strictly filtered algebras. So this is the base of the universal object theory. But furthermore, there's some compatibility between them. So compatibility is the following. We have a diagram like this. So we've got strictly filtered algebras. BU blank. So that we know that there's a natural transformation of this into the quantization functor. And then we have two natural transformations here, which go from these two functors to or BU into blank. So this is slightly subtle. These are still functors from strictly filtered algebras. But all they do is they take the morphism of strictly filtered algebras and take its associated gradient, and then you get a hom of this form. And this goes to PGA. So that ends the sort of the abstract nonsense. But let me state some consequences. So one of them is that
I mean, Losif proved that the universal quantization was given by this base. So that means that if you have any quantization, then it can be obtained by base. And so what you're saying is you added to this that you defined a quantization functor.
yeah, exactly, yeah. But there's a little bit more that comes out of it in the next section. But yeah, essentially, we added to it the quantization functor, rewrote his theorem like this with sort of more detail that we can understand. The compatibility condition wasn't explained in a lot of detail in Losif's paper. In fact, it's just one line in the statement of the main theorem. And then he doesn't really mention anything else about it. It just falls from his construction, he says. But in our paper, we kind of explore what this means quite carefully. And we explore its consequences. So one of the consequences is that there is a unique let's say AU IXU QK BU, which quantizes universal Poisson deformation.
So why do you need to use filtered algebras which are isomorphic to associated gradient? Why can't you talk about quantizations over a more general filtered algebra?
So
would it not be universal in the bigger category of all filtered algebra?
So I mean, one thing is that I don't think you could state the compatibility between the functors here, because PDA needs to receive okay.
Surely it's still true that it's based on Losif's theorem that it's universal in the larger category of all filtered algebra. Just so happens it's represented by one that's isomorphic to its associated gradient.
I hadn't thought about that. I mean, I mean, the strictly filtered algebras should be a smaller category than all filtered algebras. There could be things which are not isomorphic to their associated gradient.
Right, exactly. Yeah, I'm saying it should still be universal in a larger category of all filtered algebras. It's represented by something which is strictly filtered.
Well, I mean, the universal property which Losif states, and we've basically expanded upon, is stated for strictly filtered algebras.
Really?
Yeah, he does need for the algebra to be. So, I mean, it's almost hidden inside the statement of his theorem. You know, the statement is not very clear, but he says that, I mean, so the compatibility between these two things, he says that you should have at some point, he basically identifies the base of the associated graded of the universal quantization with the base of the universal quantization.
Yeah, that's for sure.
And then he,
But I mean, that
Yeah.
could still be true, even if you have, if you consider more general filtered quantization
Yeah.
or more general
Yeah.
data, you could still ask that you have that they come from pullback from the universal family. Though the universal family is in a strictly filtered base.
yeah,
I
I
think
guess,
it's not true, you're saying that it just doesn't follow its theory.
well, I mean, it doesn't follow from his theorem, and I don't have an instinct for whether or not it's true. It feels like,
It did follow.
something would be breaking.
Be interesting to have a counterexample that's not true.
Yeah, certainly, yeah. I mean, it's very difficult to even construct examples, let alone counterexamples.
But surely if there's a counterexample, there's already one for like something simple, I guess so too.
Yeah, sure.
Which would surprise me, anyway, that's okay. Maybe
Yeah,
not.
I'll have to think about this after, so I can't say right now. But it's a good question, all right. So, another corollary of this is that, I think I maybe have said enough about that. So basically this was one of the main tools that we used in the work that followed. So the fact that, that Namakawa's universal Poisson deformation has unique quantization, that allowed us to say quite a lot about the rate of finite Capital arrangements. So that was my original interest as well. That was where most of my research had been for. But I think that these functors give you quite an easy way of looking at the equivariance, as I mentioned. So, how much time has passed, by the way?
Well, we started a bit late, so probably around 45 minutes have passed since we begin 45 minutes, I think.
That's fine. So now I want to consider a group of graded Poisson automorphisms. Oh,
I just want to warn everybody, there's always a chance that people will have to enter here, but I think it's not going to happen. So if they enter, then we'll have to stop.
hopefully I'll get to something catchy. There's another theorem coming up. Maybe I can say, I'll probably be able to say some of our results about finite differentials. That's the most interesting stuff for me. And then possibly we can talk more about it. So once you have a group of graded Poisson automorphisms of this coordinate ring, then you can consider the gamma equivariant deformations and quantizations. So this means that you're basically deforming this coordinate ring A together with its, or CX together with the gamma action. So if I were to draw a picture of it, so we've got spec A, this is now our deformation over some spec B, then spec A should be equipped with a gamma action, so that when you specialize to the central fiber, you recover the gamma action that you first thought of here, and it should be done in such a way that this is gamma equivariant with respect to the trivial gamma structure down. Now, you can see quite easily from the universal property of the, okay, so actually I should say that there exists equivariant functors. So you get PDCX of gamma and also QA gamma. So these functors are defined in exactly the same way as the two shaded before, but now refer to gamma equivariant objects. But because of the universal property of this universal Poisson deformation, you can show that there is a right action of gamma on the universal base. So let me just quickly say how this happens. Remember that the universal object comes equipped with a choice of isomorphism. This is the sort of tethering isomorphism between the specialization and this coordinate ring that you started with. Now, if you twist this isomorphism by any automorphism, which is just an automorphism of this coordinate ring, then you get another isomorphism. And it's not hard to see that this gives you another universal object. And so there exists a unique map of base changes, which turns this one universal object into the other. And this induces a group of automorphisms of the base itself, but the side has now changed because we're basically post-composing by gamma this tethering isomorphism. We get this right action, which just again comes from some abstract constants. But the cool thing is that this functor is represented over the base, which we'll call BU gamma, and this can be described explicitly. So this is just BU over the covariance. So we take the covariance of BU, so B dot gamma, gamma and gamma, and then B and B. And equally, the functor of equivariant quantizations of CX is also represented over the same base. And they also have compatibility. That's kind of represented here a moment ago. Now these were the basic tools that we set up in the first paper, in the first half of the first paper, and then we applied them for some interesting examples in the second half.
So the technical values are also.
Oh, yeah, he needs the camera back. Right, do you need it back now? Okay, keep it on. Yeah, you do.
I mean, how long are you talking?
I'll be another 15 minutes. Is it all right? Or you
Yeah, okay.
you don't mind?
No problem.
Thanks.
Thank you.
Got an extension. Like this.
So, are there any questions about this so far? It's sort of straightforward. Now we can actually get to some interesting geometric projects. So, as I say, I've spent a lot of my research interest studying these finite W algebras. So I'll have to say just a little bit about what they are. So we take a nilpotent element in our complex set. And then we can include this into an SL2 trim. That's the theorem of Jacobs and Morozov. Which says that if you take any nilpotent element, then you can always find some subalgebra isomorphic to SL2, which has this nilpotent element as your sort of nilpositive. And these unique up to basically the conjugacy classes of such SL2 triples. They correspond to the orbits, nilpotent orbits. Now, if we let V be any adH complement to image of E inside G. So typical examples would be where if you take the centralizer of F, and you get a complement to the image of G. There's also a more traditional, there's an older construction in type A due to constant, these companion matrices. And there are a couple of other ways of, that people have thought about introducing slices to this nilpotent orbit. But essentially, the only thing you need is this. It just has to be some adH complement all of these have the same Poisson structure on the slice. So, the slice that I'm talking about is this thing E plus B. So this is transversal to the orbit. This is the tangent space of the orbit here, and this is a complement to this tangent space by construction. This thing under the K identification. So this is contained inside G, and then we get something that I'll denote SE contained inside G star. Okay, so this is the Slodowy slice. Now it's not a Poisson subvariety of G star, but it was noted by Gann and Ginsberg, sort of building on some work of Bremitz in 2002, both the papers came out at the same time. But the coordinate ring of this slice, this admits a Poisson structure by Hamiltonian reduction. So Gann and Ginsberg really talked about Hamiltonian reduction. Bremitz had constructed a quantization of this slice using representation theory and positive characteristic. They were looking at the same non-commutative algebra, but Gann and Ginsberg probably sort of viewed it more systematically by first of all constructing the Poisson structure by Hamiltonian reduction, and then looking at the quantization. So, is it Ginsberg? Am I pronouncing it wrong?
Well, it's an eel.
URG.
So URG. Victor Ginsberg, yes.
Yeah, that's right.
No. Have you got a Ginsberg as well?
There's even at least 2 Victor Ginsbergs in mathematics.
Let's see.
The both work in Poisson.
Yeah, they both use into the Poisson. Yeah. So this result you had on that board is saying you have the universal deformation of something, you have an automorphism of something, and the universal deformation of the space together with the automorphism are the universal deformations of the original thing, which are fixed by the automorphism.
Exactly.
So you look inside of your base for the universal deformation, your automorphism of your space defines therefore a composite deformation by deforming together with the automorphism, and you ask whether it's isomorphic. The deformation of the X is isomorphic to the image under automorphism. And so you look restrict to that locus where your deformations are simultaneously deformations of X and of its automorphism.
Yeah.
And that's what you're doing, right?
Exactly.
This is probably quite general.
It is,
Want to
yeah.
define, you
Yeah.
have a universal deformation of any sort of object, and you want to define the sublocus where that's a universal deformation of it together with automorphism. You look at the fixed locus for the base of this automorphism.
Yeah. So I mean, in fact, the things I said here, they could be applied to any representable functor from algebras into sets or
Right.
filtered algebras into sets.
Okay.
So there's also this natural quantization, and you basically so Hamiltonian reduction is some process of taking a sum point of Poisson, which magically inherits a Poisson structure, and you just apply the same thing as the most stupid way you can to the enveloping algebra. You take a subquotient of this, and magically it has an algebra structure which quantizes this. And I'm not telling you what the grading is. This is not the same as the grading on CG star. So one connection to equivarieties is a theorem of Maffei, which says that if you take the Slodowy slice in type A and you take the nilpotent parts, then this is actually isomorphic to a certain Nakajima equivariety because of conjecture of Nakajima. I don't think that holds in other types species and exceptional types. But there is some.
There's a conjecture, Nakajima, that these are also given by equivarieties in type A. You say?
No, it was conjectured a long time ago, and then it was proven by Maffei,
Right.
probably about 20
So you
years.
think it was conjectured by Nakajima?
Yeah.
Oh, didn't know that.
Yeah.
There is a reference to the giant short page,
Mhm.
two-page paper. So people reference this.
I see. Okay.
Yeah, I don't know if it's acceptable.
Kornheimer
Kornheimer,
proved, you say that he proved the connection between nilpotent Slodowy varieties and Equivariant varieties?
I don't know if you prove, but he mentions this. It's a very short paper, so it's hard to.
Yeah.
Um,
Yeah, it's been mentioned quite a lot in our reading group.
In any case, we know already. Most of the people here have seen already this relationship with the quiver varieties.
Okay, great.
Okay, you're saying that, so for, classical algebras, we have many examples. You know that we cannot cover all of them, but we have plenty of examples.
Okay.
So I guess the point is that you can, it's not always correct. There are many cases where you could be very explicit.
Okay. Yeah.
And actually, we have some cases with exceptional.
Already.
Kind of isolated. Very specific.
Interesting.
We can go with those.
I think that Michael will probably be back soon, just a warning, so
Yeah. So
we can continue a bit longer, but we may come and take the camera.
Yeah.
Warn
Okay.
everybody.
Well, I'll stop whenever. I don't mind. Let me just carry on for a moment longer for now. So this is a conic symplectic singularity. So the resolution of this variety is just the restriction of this string of resolution. It's a pre-image over this slice. And the normality is just a result of the normality of a null cone here. The second point is that you can consider this slice here, which is a Poisson variety, although this is the subvariety of G star, certainly the Poisson structure here comes from actually what I want to say is that so this clears into G star and this maps down to here. This is H star over W. And you can consider the restriction of this adjoint quotient to the Slodowy slice. And this is a graded Poisson deformation. Of the nilpotent part. So the central point, again, I'm not telling you exactly what the grading is, it's called the cash-down grading, cash-down filtration on here. So, and also the finite W algebra is quantization of a graded Poisson deformation. So I suppose the next part, I'm going to sort of list lots of results and explain how we built on them. So I don't know whether it's worth starting to list them and then stopping straight away. Perhaps it's better to stop now. I mean, I can carry on if you like. I don't mind. What would you prefer?
Well, I mean. If you had something else to say, I'd just take a few minutes until Michael.
Yeah, okay.
Otherwise, we should probably stop.
Okay. So I can just say something, it'll take a couple of minutes. So there was this conjecture of growth and deep proven by Briscoe. And in 1980, and it said that no, sorry, it's the
71.
71, thank you. Okay. 71. It says that inside the subregular slice, the subregular nilpotent slice is a Duval Quinian singularity. Again, at the same time, so it's kind of exactly the same type A, B, B. So if you take the subregular nilpotent orbit, it has codimension 2 inside the nilpotent cone. So when you take this transverse slice to the closure of the regular orbit, then you're going to have an isolated singularity of dimension 2. This is actually a rational surface singularity, so some general theorems tell you that it has to be one of these finding singularities, and the lovely thing is that the Deakin diagram snapshot. It's a very famous statement.
And the non-theoretical, it's.
Yes.
Monodromy that analysis.
Exactly, yeah. I mean, I actually don't understand it in terms of monodromy. I read Slodowy's book quite a lot, and I'd like to know more about Travis's perspective on this. So Slodovy wrote a book in the 1980s, which was about this, and he, I suppose, the main original contribution to what Briscoe had already done was considering the subregular slices in types B, C, F, G. So these are, so I'll call it N in naught. To AD singularity. So by the same line of reasoning that I just sketched a moment ago, it has to be an AD singularity. The question is which one is. So if you take G naught, this is the BCFG non-simply based guy. So BN, CN, or G2, these go to the following one. So A2n minus 1, Bn plus 1. I think Travis even mentioned this.
Yeah,
Pairings a moment ago, yeah.
without the indices, but you can count them.
And at the time, of course, there wasn't a theory of universal Poisson deformations, but for isolated surface singularities, there was this theory of versal deformations with respect to, okay, so versal deformations of these particular types of singularity. And Slodowy showed that these ones on the left are actually the equivariant versal deformations with respect to the Deakin automorphisms coming from the simply laced guy. So not only is the central fiber of this deformation isomorphic to the guy up there, but the entire subregular slice is the gamma versal deformation for this. So let me write that down. So S E naught is the let's say out G, these guys here, it's the G side, and that's the G naught side. It's the out G versal deformation of so shall I just carry on into the prompts?
And this was a Slodowy proved this statement.
Yeah. So this section is
Okay.
in section 8 of Slodowy's book.
Yeah, I mean. Can go for maybe another few minutes. Stop and have lunch.
Yeah. Okay. Sounds good.
Maybe you can try to tell us,
Yeah.
you can maybe try to tell us your punchline about the two realizations of this. Nilpotent, the orbital on the mirror and on the
Okay. Yeah. I can try and do that. Yeah. So I mean, basically, if you try to leave the subregular setting, then there's no theory of versal deformations, but now we do have the theory of Poisson deformations, universal Poisson deformations. Then Namikawa Soga studied when is the Slodowy slice actually the universal Poisson deformation of Namikawa. And they said that it always holds with some sort of notable exceptions, and the exceptions fall into a few families. So the subregular in type BCFG is one obvious family where you have to have exceptions. But there were also some kind of weird exceptions. So 2 blocks in type C and dimension 8 in type G. And so I wanted to sort of study these more carefully. I mean, one thing that we did do in this paper with 4 authors is we looked at the subregular case, and we were able to show that. So I mean, the gamma equivariant story hadn't appeared in sort of previous work of Namikawa or Namikawa Soga, so they didn't have a way of formulating this this kind of possible theorem. I mean, they say that if you have G naught subregular, so G naught CFG, you look at the subregular here, then one of our results is that the slightly sliced here is the universal G equivariant Poisson deformation, and then similarly for the finite W algebra UG. Now, one nice application of this was that people have been trying to understand presentations of these W algebras for a long time, because they're just some subquotient of the enveloping algebra. It's very difficult to write down precise generators of relations, but in type A, people found a precise relationship via these shifted Yangians. And extending this to other types has been a kind of long-running project of mine, which is starting to pick up pace now. But we were able to, so for the subregular in type B, we were able to take this Yangian presentation of the subregular in type A, and then just take we knew what the quotient should be that would give you the W algebra in type B. It's just the covariance by this group action gamma. And we were able to pin exactly what this does on the level of the Yangian presentation. So that was one of the applications in type B at the end of that paper. But then after this, I worked with Filippo on the type C parts. I just mean that the partition had two parts. There are two Jordan blocks beyond nilpotent elements, and we did quite a lot of work on this.
So what is there more to say about the subregular case? I thought everything was known about the subregular case.
Well, this isn't stated in the language of
Poisson.
yeah, and nor is there anything about the quantizations of this. So really, yeah, we were upgrading. We sort of sold this as a non-commutative animal,
But using the Namikawa and the Losif, this should follow just from taking the fixed locus of the base, right?
Yeah, sure. And if the proof's too easy, then you don't have to read the paper.
Well, that would be convenient for me, but I couldn't be sure that's true.
Yeah, I mean, I had to do quite a little work to get there. I mean, if it's self-evident to you, I don't mind. So that's okay.
I don't know. I have to look and see.
Yeah, have a look.
All right, great. Okay, but go ahead with what you were saying.
Yeah, so for two parts, these are maybe a bit more surprising that there are some exceptions here, but again, there's a kind of yeah.
Not sure about this is silly.
Yeah, no, I mean, it's the things that you said that kind of eloquently summarize the things that we've done. They were the things that I had to learn and kind of building to write this all together. So
Sure.
it was it's quite a long project.
All right.
But then in type C, there are these exceptions with two parts, and you can ask whether there's some similar kind of equivariant degree pokery happening with respect to type D, and it turns out that there actually is. So you take E naught is a member of the orbit, which has parts lambda 1, lambda 2. This is contained in SO2n. Then, sorry, this is E, and then you've got some other guy, E naught.
Two parts refers to the partition.
Yeah, these are the size of the Jordan blocks, lambda 1, lambda 2.
In SO2n, so they must be old.
Yeah, exactly. Yeah. So these are odd parts, unless unless you're in SO4n, and then you can have a very even orbit. And so we do have some results about that as well. The first part of the theorem holds even for these very even ones. So one of the first results in Ambrosio Topley was there's a C-star equivariant Poisson isomorphism. So we found out afterwards that this isomorphism of abstract varieties was known using Nakajima quiver varieties by Henderson Licata. So they considered involutions on the quiver variety which come from thinking diagram automorphisms. And by taking the fixed points, they were able to see these things as the fixed points of a certain type of energy.
I know to show how they did.
Do I know how to show it? I'm afraid not, no.
Yeah, it would be nice to see the quiver segments.
Yeah, no, I'm afraid I'm only just learning about quivers now, so I can't say anything more.
What was the result of Henderson?
So they threw this as abstract varieties. Yeah.
Upgraded.
We upgraded into Poisson varieties, yeah.
Sure.
And
So I know some of it. These were in D and C.
yeah, exactly, D and C. So this was in 2014. We can show you the section in the paper. But the existence of a Poisson isomorphism was sort of key to what we wanted to do. So we were interested in understanding whether these types C things could be seen as an equivariant deformation, whether the slice is an equivariant deformation of its nilpotent part. And the answer is yes, but we actually have to exclude these cases where lambda 1 is equal to lambda 2. So the main result in AT, we exclude that lambda 1 is equal to lambda 2 even. And the reason is that I've been formulating this in terms of the outer automorphism. Particularly what I mean here is the splitting of the outer automorphism group, the splitting which preserves the slice in question. So it's very important. This itself doesn't actually act under the algebra. So when the outer automorphism group doesn't preserve the nilpotent orbits, and therefore it doesn't preserve the slice. If you look at these cases, lambda 1 is equal to lambda 2 is the very even orbit which is muted by outer automorphisms. And in this case, so with this exclusion, we show that SE naught goes to H star naught over W naught, which is the G equivariant Poisson definition. Universal Poisson definition. And of course, the equivariant quantization has this uniqueness property that I mentioned, and the same result holds for the W algebra.
What does exclude the lambda 1 equals lambda 2? What?
So this is
What is the word?
so this excludes the lambda 1 equals lambda 2 even case.
Oh, okay.
So we have to exclude those because those are the very even orbits. Okay, so
I need to give back the camera.
yeah. And then
Just a second. All right, yeah, I give you the camera. Sorry about that. Okay, so I will take away the camera. Sorry for those of you who are online.
Who is the other side?
It's how do you say his name? Yeah, and also a organization. Thank you very much.
Oh, but not both. One is one.
Paul is not. Exactly. So,
do you want me to carry on a little bit, or should we break for lunch?
Go for lunch and discuss around.
yeah, let's
That sounds good, yeah.
Yeah, I have to teach it. I don't know. So,
Oh.
Yeah.
So your students is the Tiziano and then the Chinese.
yeah, it's yeah. So we have yes, I have Wei, and I have Zerui now as well, and Tiziano, so three. And Yuan is also on one thing was yeah, that's good.
I want the girl. No.
Boy always wear a mask.
Said you want.